Semiconductors and insulators have an almost completely full band. So there are full states down in this band here, full of electrons. And we call that the valence band. Separated by a band gap energy, so some amount of energy here, usually called Eg, from an almost completely empty band. So we've shown the empty circles here to show the potential electron states, but we're saying that there are almost none of those states actually occupied with electrons. So these would be empty states. And this we call the conduction band. Note that an empty band rather obviously does not conduct electricity. There are no mobile electrons that could move. Also, perhaps much more surprisingly, a full band does not conduct electricity either. The reason for that is that the electrons cannot change their states within this band. All of the states are full, so there can't be any change in the motion of the electrons. There's nowhere for them to go, and as a result, there's nothing that allows us to conduct electricity. The difference between semiconductors and insulators is primarily that insulators have such a large band gap energy that there is negligible thermal excitation of electrons from the valence band to the conduction band. And so these two bands remain respectively almost completely empty and almost completely full, so there's really no conduction. At finite temperatures in a semiconductor, a small number of electrons can be excited from the valence band to the conduction band. So thermal energy alone is sufficient to take some of these electrons and put them up there, leaving behind absences of electrons here and electrons up there. These electrons in the conduction band and the absences of electrons in the valence band, which we typically call holes, can conduct electricity within their bands. These electrons are obviously free to move. There's states they can go into, so they can change their velocities. And similarly, these holes have states that they can go into. These absences of electrons can be moved to other states. And as a result, we can conduct electricity within both bands. So, semiconductor materials, because of their narrower band gap energies and the consequent thermal excitation of a few carriers from one band to the other, can conduct electricity somewhat weakly, hence the name semiconductor. Now, with semiconductors, we can do what's called doping. We can substitute a few atoms that each have more electrons, such as, for example, adding a group 5 element, like phosphorus, in place of a silicon atom in what is otherwise a group 4 semiconductor, like silicon. So here we've added in some group 5 elements, they give us extra electrons, and what tends to happen is that those appear in the conduction band where they can now conduct. And this is known as N-type doping, N for negative. It makes the material conduct more because of these additional electrons. Substituting a few atoms that have fewer electrons, such as putting a group 3 element like boron in place of one of the silicon atoms in the group 4 semiconductor silicon, is known as P-type doping, P for positive. So here we now have some holes here where we're short of an electron in these various group 3 elements here, and what's happened is the electrons come out of the valence band to make up that deficiency, and that makes the material also conduct more because we now have some holes down in the valence band that are able to conduct. If the lowest minimum in the conduction band is above the highest maximum in the valence band, the semiconductor is said to have a direct gap. So the highest point in the valence band and the lowest point in the conduction band are at the same K value. Direct gaps are particularly important for light emitters. Electrons can perhaps be pumped into the conduction band, and if we do that, they may gather near this lowest minimum here. And similarly, we might manage to pump some holes into the valence band, and they would gather near the highest maximum. It's good to think about holes as bubbling up towards the top of the band. The electrons are falling down, the holes are actually bubbling up here. And then an electron can possibly fall vertically to fill in that hole. And as it does so, it may emit a photon. And this process of emitting photons works much better if the electrons are directly above the empty electron states or hole states in the valence band. That's called a direct transition. In an indirect gap semiconductor, and both silicon and germanium are indirect gap semiconductors, the lowest conduction band minimum, or possibly many different minima, is not directly above the highest valence band maximum here. This process of light emission is much weaker. Non-vertical transitions, as they're called, of photon emission are relatively weak. So indirect gap semiconductors typically do not make good light emitters. The difference between metals and semiconductors and insulators is that in a metal, because of the number of electrons in the metal atoms, the lowest conduction band can be partially full of electrons, for example, half full, even at zero temperatures. It's because of the number of electrons in the outer shells of the atoms, essentially. Hence, metals can conduct electricity well at essentially all temperatures, at least compared to semiconductors and insulators.